Every large moon in this solar system follows one rule. It orbits its planet in the same direction the planet spins. Every single one, except one. 4.5 billion kilometers from Earth, a world larger than Pluto circles Neptune backward. It moves against the planet's rotation, against the motion of every other major satellite ever observed. That single fact forced scientists into a disturbing conclusion. This moon should not be here. Triton is not a moon that grew beside Neptune. It is a captured world, likely stolen from the Kuiper Belt, dragged into orbit by gravity, and frozen into a backward path that has been slowly reshaping Neptune's entire moon system ever since. This is the story of the moon that does not belong. If this kind of deep dive into the strange corners of our solar system sounds like your thing, a like and a subscribe would mean the world to us. It helps more people find stories like this one. Now, settle in, get yourself comfortable. Let's begin. Something is wrong with Neptune's largest moon. Not with its surface, not with its size, not with how it looks through a telescope. Something is wrong with the direction it moves, and that single wrongness changes everything we think we know about this world. Every large moon around every giant planet in this solar system orbits the same way, prograde, forward, in the same direction the planet spins. This is not a trend. It is not a pattern with interesting exceptions. It is the direct physical consequence of how moons form. When a giant planet coalesces out of a collapsing cloud of gas and dust, the material settles into a spinning disk around the young world. Everything rotates together. The planet turns. The disk turns with it. Moons condense out of that disk, accreting from the same pool of material, inheriting the same angular momentum, orbiting in the same direction the planet rotates. Forward motion is not a choice. It is the default. It is the only way a large moon can form in place around a giant planet. A moon born in a circumplanetary disk orbits prograde because the physics of formation gives it no other option. Jupiter's 4 great moons demonstrate this perfectly. Io, Europa, Ganymede, and Callisto, the Galilean satellites orbit prograde in a neat formation close to Jupiter's equatorial plane. They are spaced at remarkably regular intervals, and 3 of them are locked in an orbital resonance that has persisted for billions of years. These moons formed alongside Jupiter, and their orderly configuration is the proof. Saturn tells the same story. Titan, the second largest moon in the solar system, at 5,150 kilometers in diameter, orbits prograde. So do Rhea, Dione, Tethys, Iapetus, Enceladus, and Mimas. Saturn possesses one of the richest satellite systems in the solar system, with 146 known moons, and every single one of its large and mid-sized members orbits forward. Uranus pushes the rule to its extreme and still obeys it. The planet is tipped almost completely on its side, with an axial tilt of approximately 98 degrees. Whatever ancient collision knocked Uranus sideways should have scrambled everything around it. But the 5 major moons Miranda, Ariel, Umbriel, Titania, and Oberon orbit prograde, aligned with the planet's tilted equator. They followed the planet when it fell. They kept formation. The rule held. Across 4 giant planets, across more than 24 large and mid-sized satellites, the pattern is unbroken. Large moons orbit forward. They form in place. They belong to their planets in the deepest physical sense, sharing a common origin and a common rotation. Triton breaks this rule completely. Neptune's largest moon circles the planet backward. Its orbital inclination measures approximately 157 degrees relative to Neptune's equatorial plane, which in practical terms means it travels in the opposite direction to Neptune's rotation. Retrograde, against the spin, against every other major satellite ever observed around any planet in this solar system, Triton is not merely tilted or slightly off-axis, it is fully reversed. It moves the wrong way. And Triton is not a small captured fragment. It is approximately 2,710 kilometers in diameter. That makes it larger than the dwarf planet Pluto, larger than the dwarf planet Eris. It is the 7th largest moon in this entire solar system. a world massive enough to be rounded by its own gravity, massive enough to hold a thin atmosphere, massive enough to drive geological processes on its surface. A body this large in a retrograde orbit around a giant planet is not unusual. It is, by every understood mechanism of moon formation, impossible. This single orbital fact is the engine of the entire story. To understand why a backward orbit matters so deeply, you have to understand what it means for the relationship between a moon and its planet. A prograde moon exists in a kind of gravitational partnership with its host world. Both rotate in the same direction. Tidal forces, the stretching and flexing caused by gravity acting differently across a body's near and far sides, transfer energy from the planet's rotation into the moon's orbit. Over billions of years, this energy transfer pushes the moon outward. The orbit slowly expands. The moon gradually recedes from the planet. Earth's moon is a perfect example. It orbits prograde. Tidal interactions with Earth are slowly pushing it away at a rate of approximately 3.8 centimeters per year. That sounds tiny, and in a human lifetime it is undetectable. But over geological time, the effect is enormous. The moon was once much closer to Earth than it is today. Tidal energy transfer has been steadily widening its orbit for 4.5 billion years. This is the normal life cycle of a large prograde satellite. Cooperative, gentle, stable across timescales that dwarf the entire history of life on Earth. A retrograde moon reverses every part of this dynamic. Instead of sharing the planet's rotational direction, it opposes it. The tidal interaction does not add energy to the moon's orbit, it removes energy. The moon does not spiral outward, it spirals inward. Every revolution bleeds a little more angular momentum from the system. The orbit shrinks, slowly but relentlessly. The moon edges closer to the planet with each passing geological epoch. This process has a terminal point. If a retrograde moon spirals inward far enough, it eventually crosses a boundary called the Roche limit, the critical distance at which the planet's tidal forces become stronger than the moon's own gravitational self-cohesion. Inside the Roche limit, a moon cannot hold itself together. It is stretched, deformed, and ultimately torn apart. The debris spreads into a ring. The moon ceases to exist as a coherent world. This means that a large retrograde orbit is inherently self-destructive. It is not a permanent arrangement, it is a countdown. A clock that has been running since the moment the moon entered that backward path. Triton is on this countdown right now. Its orbit is shrinking. The rate of shrinkage depends on how efficiently tidal energy dissipates inside Neptune's interior, a quantity that is extremely difficult to measure from 4.5 billion kilometers away, and one that scientists have revised repeatedly as models improved. Early estimates were alarming. Some calculations suggested Triton would reach Neptune's Roche limit in roughly 3.6 billion years. This was a dramatic timeline shorter than the Sun's remaining lifespan. It implied that Neptune might one day gain a ring system as spectacular as Saturn's, assembled from the shattered remnants of a world larger than Pluto. The idea captured imaginations. A moon torn to pieces, becoming a ring, a world unmade by the same gravity that captured it. But a 2025 study revised this prediction substantially. Improved modelling of Neptune's tidal dissipation showed that the orbital decay is far gentler than earlier calculations assumed. Under updated parameters, Triton will not reach Neptune's Roche limit for approximately 28 billion years, more than 6 times the current age of the solar system, and many times longer than the remaining main sequence lifetime of the Sun. Triton's destruction is real. It is written into the physics of its orbit, but it is so far in the future that it belongs to an era of the cosmos that no currently existing star will live to witness. The critical point is not Triton's fate. It is what the retrograde orbit reveals about Triton's past. A moon this massive cannot form in a retrograde orbit. The physics of circumplanetary disk accretion does not allow it. When large moons grow out of the material orbiting a newly formed planet, they inherit the disk's angular momentum. They orbit forward. There is no formation mechanism, no known process, that produces a body 2,710 kilometers across in a backward path around its planet from birth. Small retrograde objects are common. All 4 giant planets have populations of tiny irregular moons, captured asteroids and cometary fragments. typically a few kilometers across, tumbling along tilted, eccentric, and retrograde orbits at great distances from their planets. These are gravitational prisoners, debris snagged during close encounters with passing small bodies. Their retrograde orbits are the direct signature of capture, and nobody finds them surprising. A 10-kilometer rock in a backward orbit is an expected feature of a giant planet's extended gravitational neighborhood, but Triton is not a 10-kilometer rock. It is a world. It is nearly 3,000 kilometers across. It has a differentiated interior with a rocky core, an icy mantle, and a frozen surface. It holds an atmosphere. It is geologically active. No process captures a body that large casually, and no process forms a body that large in a retrograde orbit. The combination of Triton's enormous size and its backward motion is the single most powerful piece of evidence in all of planetary science that this moon was not born where it now resides. Triton formed somewhere else. It spent some portion of its early existence as a free body in its own independent orbit around the Sun, and then, at some point in the solar system's history, Neptune's gravity captured it, pulling it onto a bound retrograde orbit from which it has never escaped. This is not a speculative hypothesis. It is the consensus interpretation among planetary scientists. The debate about Triton is not whether it was captured. That is considered effectively settled by the retrograde orbit alone. The debate is about how the capture happened, what mechanism allowed Neptune to grab a free-flying world this large and keep it. But before we get to the how, look at what Triton's capture did to the system it invaded. Compare Neptune's moons to those of the other giant planets, and the destruction becomes obvious. Jupiter has 95 known moons. 4 of them are enormous, the Galilean satellites ranging from approximately 3,100 to 5,260 kilometers in diameter. They orbit in orderly prograde paths near Jupiter's equator, structured and stable. Beyond them, a swarm of smaller, irregular moons occupies distant orbits. The system is rich at every scale. Saturn has 146 known moons. Titan dominates at over 5,000 kilometers, but 6 other mid-sized satellites between approximately 400 and 1,500 kilometers fill out a robust prograde system. Add the spectacular rings and the tiny shepherd moons, and Saturn's neighborhood is one of the most complex and densely populated environments in the solar system. Uranus has 27 known moons. 5 are substantial Miranda through Oberon, ranging from approximately 470 to 1,580 kilometers. Despite the planet's extreme axial tilt, the system is ordered. Multiple mid-sized prograde moons spaced across a range of orbital distances, exactly what formation models predict for an ice giant. Now look at Neptune. 16 known moons. Triton accounts for more than 99.5% of the total mass orbiting the planet. Everything else put together, all 15 other moons combined, adds up to less than half of 1% of the system's satellite mass. The next largest moon, Proteus, is only about 420 kilometers across, less than 1/6 of Triton's diameter. After Proteus, the moons shrink rapidly. Nereid, with its wildly eccentric orbit, and then a handful of tiny inner satellites, Naiad, Thalassa, Despina, Galatea, Larissa, Hippocamp, most of which appear in Voyager. 2 images as small, irregularly shaped, battered objects, not intact primordial worlds, fragments. Neptune's system is lopsided in a way that no other giant planet's system is. One colossal retrograde intruder dominates everything. The rest is debris, the family of mid-sized prograde moons that Neptune should have the family that Uranus actually has is missing. Either it never formed, which contradicts everything we understand about moon formation around ice giants, or it formed and was subsequently destroyed. The evidence points overwhelmingly to destruction, and Triton is the prime suspect. In August of 1989, NASA's Voyager 2 spacecraft arrived at Neptune after 12 years of traveling across the outer solar system. It was the last planetary encounter of the mission's grand tour. A once-in-a-lifetime alignment of the giant planets had allowed a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune in succession, using each planet's gravity to slingshot toward the next. There was no option to orbit. No chance to linger. Voyager 2 would pass through the Neptune system once, gather what data it could, and then continue outward into the void, never to return to any planet. The encounter was the result of a deliberate and irreversible choice. Mission planners had to decide between two trajectories at Neptune. One would have kept Voyager 2 near the ecliptic plane, the flat disk in which the planets orbit, preserving the theoretical possibility of a future encounter with another object. The other would send the spacecraft diving close to Triton, passing within approximately 40,000 kilometers of the Moon's surface, but deflecting Voyager 2's path sharply below the ecliptic. There would be no coming back from that deflection, no future planetary flyby. Choosing Triton meant ending the Grand Tour's planetary mission forever. They chose Triton. The scientists and engineers who planned the encounter judged that a close pass of Neptune's strange, backward moon was worth more than any hypothetical future target. That decision shaped everything we know about this world. The flyby itself was an exercise in precision under impossible constraints. Voyager 2 was travelling at approximately 27 kilometers per second, roughly 97,000 kilometers per hour relative to Triton. At that velocity, the window of close approach lasted only a few hours. The spacecraft had no ability to slow down, stop, or turn around. It was a single pass at enormous speed, and every observation had to count. Making matters harder, Neptune orbits 4.5 billion kilometers from Earth. Radio signals travelling at the speed of light required more than 4 hours to cross that distance. This meant there could be no real-time control of the spacecraft during the encounter. Every camera sequence, every instrument pointing, every data recording command had to be uploaded hours in advance and executed autonomously by the spacecraft's onboard computers. If something went wrong, a misaligned instrument, a timing error, a data storage glitch, there was no way to correct it before the encounter was over. The entire scientific return from the only close visit to Triton in human history depended on software written years earlier, performing flawlessly at a distance where no human intervention was possible. It performed flawlessly. Voyager 2 confirmed the retrograde orbit through precise trajectory tracking. It measured Triton's size, mass, and density, establishing it as a dense, differentiated body with a core of rock and metal wrapped in a mantle and crust of water ice. It detected a surface covered in frozen nitrogen, with methane ice, carbon monoxide ice, carbon dioxide ice, and water ice also present. It recorded a surface temperature of approximately 38 Kelvin, minus 235 degrees Celsius, confirming Triton as the coldest measured surface of any body in the solar system at that time. Then it found the geysers. Dark plumes of material were erupting from the icy surface. Columns of dark particles and gas shooting vertically upward, reaching miles into the thin atmosphere, then fanning out into clouds that drifted downwind and deposited dark streaks across the bright nitrogen frost. On a world where nitrogen exists as ice, where temperatures hover barely above absolute zero, where solar energy is roughly 900 times weaker than at Earth, something was launching material high into the sky. The images captured multiple active eruptions. Nobody had expected this. Nothing in the outer solar system had prepared scientists for a frozen moon with geysers. The surface itself was equally confounding. Triton showed astonishingly few impact craters. In a solar system where cratered, battered surfaces are the hallmark of ancient, geologically dead worlds, Triton's terrain looked fresh. Estimates based on crater density suggest the visible surface is only approximately 10 to 100 million years old, staggeringly young. For a moon that has existed for 4.5 billion years, something has been resurfacing this world, erasing craters, laying down new material. Something is still working. Voyager 2 revealed terrain types found nowhere else. A strange, dimpled landscape, nicknamed cantaloupe terrain, for its resemblance to melon skin, covering extensive areas of the imaged hemisphere. Smooth, frozen plains suggested past flows of cryogenic material. Ridges and fractures hinted at tectonic forces. Everything pointed to a world that had been geologically active in the recent past and might still be active today. But Voyager 2 imaged only approximately 40% of Triton's surface. The remaining 60%, the hemisphere facing away during the flyby, has never been seen by any spacecraft. It remains the largest unexplored solid surface in the solar system, closer than the Kuiper Belt. We do not know what lies there. We do not know whether more geysers erupt on the far side, whether the cantaloupe terrain extends across the entire globe, or whether entirely different geological features wait in the darkness. And the instruments Voyager 2 carried were designed in the 1970s. They could not measure magnetic field variations with the precision needed to detect the subtle signature of a subsurface ocean beneath the ice. They could not chemically analyze the plume material to search for salts, organics, or other markers of interior processes. They could not map surface composition at the resolution modern planetary science demands. The spacecraft gave us an astonishing first glimpse of Triton and then vanished into the outer solar system, leaving behind more questions than answers. As of 2026, no mission has returned to Neptune or Triton. No spacecraft is currently funded or scheduled to visit the Neptunian system. Everything we have learned about Triton's interior, its possible ocean, the energy sources driving its activity, and the detailed history of its capture relies on that single flyby's data, combined with ground-based and space telescope observations conducted from billions of kilometers away. More than 36 years after Voyager 2's brief encounter, we are still trying to understand what it showed us. Here is what we know. A world larger than Pluto orbits Neptune backward. Its surface is impossibly young. Geysers erupt from its frozen plains. A thin nitrogen atmosphere clings to its surface. Its composition links it not to Neptune but to the icy bodies of the distant Kuiper Belt. And the moon system around Neptune looks like it was demolished. The retrograde orbit is the key that unlocks the rest. It tells us Triton was not born here. It was captured. It came from somewhere else. And if a world this large was pulled into orbit around Neptune, it did not arrive quietly. The capture must have involved unimaginable gravitational violence, the kind of violence that could erase an entire existing moon system and reshape a planet's satellite neighborhood from the ground up. Now the story follows Triton backward through time, to the frozen reservoir of icy worlds where it was born, to the planetary twin it left behind, and to the catastrophic moment when Neptune's gravity reached out and stole it. Beyond the orbit of Neptune, the solar system does not end. It changes. Inside Neptune's orbit, the solar system is structured. Planets follow nearly circular paths in a flat plane. Rocky worlds hug the inner region. Gas and ice giants dominate the middle and outer zones. Moons, asteroids, and comets fill the gaps. There is a sense of architecture to it, an order that emerged from the physics of a collapsing cloud of gas and dust 4.5 billion years ago. Beyond Neptune, that order dissolves. The Kuiper Belt begins at roughly 30 astronomical units from the Sun, the distance of Neptune's orbit, and stretches outward to approximately 50 astronomical units. 1 astronomical unit equals the distance between the Earth and the Sun, roughly 150 million kilometers. At 30 astronomical units, sunlight is 900 times weaker than at Earth. Temperatures hover around 40 to 50 Kelvin. At these distances, volatiles that would be gases in the inner solar system, nitrogen, methane, carbon monoxide, ammonia, exist as solid ices. The Kuiper Belt is a frozen reservoir of primordial material, icy bodies left over from the era of planet formation, never assembled into a full planet, scattered and preserved in the deep cold of the outer solar system. If the structured inner solar system is a city organized, dense, governed by clear rules, then the Kuiper Belt is the sparse countryside beyond the last highway. Scattered objects drift through vast, empty spaces. Interactions are rare. The population is thin but enormous in extent, stretching across billions of kilometers of frigid darkness. The Kuiper Belt is home to some of the most fascinating objects in our solar system. Pluto, the most famous dwarf planet, orbits here. So does Eris, slightly more massive than Pluto but slightly smaller in diameter. Marke, Haumea, and Quaoar round out the known population of dwarf planets, worlds massive enough to be shaped into spheres by their own gravity, but too small and too distant to have cleared their orbital neighborhoods the way the 8 major planets have. Triton almost certainly came from this population, but to understand how Neptune captured a Kuiper Belt world, you first have to understand something that would have seemed absurd to planetary scientists 50 years ago. Neptune did not form where it orbits today. the giant planets of the solar system were not always arranged the way we see them now. In the earliest epoch of the solar system's history, the first few 100 million years after the Sun ignited, the giant planets orbited closer to the Sun and closer to each other than they do today. Jupiter, Saturn, Uranus, and Neptune were packed into a more compact configuration, with Neptune likely forming somewhere between 15 and 20 astronomical units from the Sun, rather than at its current distance of 30. What changed everything was a period of gravitational upheaval known as planetary migration. Gravitational interactions between the giant planets and the massive disk of small icy bodies that surrounded them caused the planets' orbits to shift. Jupiter migrated slightly inward. Saturn, Uranus, and Neptune migrated outward. The process was not smooth. Dynamical models, particularly the widely studied framework, developed in the early 2000s by researchers in the French city of Nice, and consequently called the Nice model, showed that at some point, the migration became chaotic. Jupiter and Saturn crossed a mutual orbital resonance that destabilized the entire outer solar system. Neptune was flung outward, ploughing through the dense primordial Kuiper Belt like a gravitational bulldozer. This was not a gentle drift. Neptune's outward migration scattered the Kuiper Belt violently. The belt had originally been far more massive and more densely populated than it is today, perhaps containing 30 to 50 Earth masses of icy material. As Neptune swept through, its gravity hurled the vast majority of that mass onto wildly different orbits. Some objects were flung inward, toward the inner solar system. Some were ejected entirely, cast into interstellar space. Some were pushed outward into more distant, eccentric orbits. Only a small fraction of the original Kuiper Belt population survived in stable orbits. The remnant we observe today, this migration epoch, is essential context for Triton's capture. Neptune was not sitting at 30 astronomical units, peacefully waiting for a Kuiper Belt object to wander by. Neptune was charging through the densest part of the icy disk, encountering thousands of large bodies at close range over millions of years. Close encounters between Neptune and Kuiper Belt objects were not rare events during this period. They were frequent, routine even. The conditions for capturing a large body, conditions that would be statistically improbable in today's sparsely populated Kuiper Belt, were common during the migration. This is what makes the capture hypothesis so physically plausible. Neptune did not need to wait for an unlikely coincidence. It was surrounded by targets. The migration created exactly the kind of chaotic, encounter-rich environment in which a capture event becomes not just possible, but expected. The evidence for a Kuiper Belt origin is not based on a single observation. It is a convergence of multiple independent lines of reasoning, each pointing to the same conclusion. First, there is the retrograde orbit itself. As we have already seen, a large moon cannot form in a retrograde orbit around a giant planet. It must have been captured from an external trajectory. The Kuiper Belt is the only plausible source reservoir for a body of Triton's size, composition, and orbital characteristics. No credible alternative origin has been proposed. Second, there is the composition. Triton's surface is dominated by frozen nitrogen, with methane ice, carbon monoxide ice, carbon dioxide ice, and water ice. This volatile inventory matches the known surface compositions of Kuiper Belt objects remarkably well. It does not match the compositions of bodies that formed in the warmer, volatile, poor inner regions of the circumplanetary disk where regular moons accrete. Triton's chemical fingerprint points outward, toward the cold reservoir beyond Neptune. Third, and most strikingly, there is Pluto. The comparison between Triton and Pluto has fascinated planetary scientists for decades, and it has only grown stronger with time. Triton is approximately 2,710 kilometers in diameter. Pluto is approximately 2,376 kilometers. The size difference is modest. Triton is roughly 14% larger. Their bulk densities are close. Triton at approximately 2.06 grams per cubic centimeter. Pluto at approximately 1.85. Both densities indicate bodies composed of a mixture of rock and ice, with Triton's slightly higher density suggesting either a somewhat larger rocky fraction or a loss of volatiles during its capture and tidal heating history. Their surface compositions are strikingly similar. Both are covered in frozen nitrogen. Both have methane and carbon monoxide ices on their surfaces. Both possess thin nitrogen atmospheres maintained by the sublimation and deposition of surface frosts. Both display complex seasonal cycles in which volatile ices migrate across the surface in response to changing solar illumination patterns over their long orbital periods. When the New Horizons spacecraft flew past Pluto in July of 2015, it transformed the comparison from abstract to vivid. For the first time, scientists could see what a large Kuiper Belt world actually looks like up close. And the resemblances to Triton were immediate. New Horizons revealed a world of startling geological complexity. Pluto's surface was not the featureless, cratered ice ball that many had expected. Instead, the spacecraft photographed vast plains of frozen nitrogen, most dramatically Sputnik Planitia, an enormous heart-shaped basin over 1,000 kilometers across, filled with slowly convecting nitrogen ice. The surface of this basin is divided into polygonal cells tens of kilometers wide, driven by convective overturn in the nitrogen ice layer. Fresh nitrogen is continuously cycling within the basin, making Sputnik Planitia one of the youngest surfaces in the outer solar system, perhaps only 10 million years old in some regions. The parallels to Triton's young, resurfaced terrain were striking. New Horizons also found mountain ranges made of water ice rising several kilometers above the surrounding plains. It detected complex organic compounds called tholins, reddish-brown molecules produced by ultraviolet radiation processing of methane and nitrogen, coating large areas of Pluto's surface. It observed glacial flows where nitrogen ice appeared to be actively moving across the terrain, filling craters and spilling through mountain passes. And it discovered that Pluto's thin nitrogen atmosphere was far more structured than expected, with distinct haze layers extending over 200 kilometers above the surface, backlit by the sun in images that became iconic within hours of their release. The world New Horizons revealed was not dead. It was active, complex and diverse, a Kuiper Belt object with a geological personality that rivaled some of the inner solar system's most interesting worlds. Now, consider what this means for Triton. Pluto is the twin that was never captured. It has spent its entire existence as a free body in the Kuiper Belt, receiving no tidal heating, no energy injection from gravitational capture, no transformation from planetary interaction, and yet it is geologically complex, with young surfaces, active volatile cycling, and processes that are still reshaping its terrain today. If the uncaptured twin is this active, what should we expect from the twin that was captured, the one that received billions of years of intense tidal heating on top of whatever intrinsic activity its composition allows? The answer is exactly what Voyager 2 found, a surface even younger than Pluto's most active regions, geysers that Pluto does not appear to possess, evidence of resurfacing processes that go beyond nitrogen ice convection into what may be full cryovolcanism driven by internal heat. Triton is Pluto with an extra energy source, the energy of capture layered on top. A 2024 study published in the Proceedings of the National Academy of Sciences modelled volatile transport on both Pluto and Triton using identical initial conditions and the same volatile inventories. The study showed that the major differences in their surface appearances, Pluto's dramatic contrast between bright nitrogen glaciers and dark organic terrain, versus Triton's more uniformly bright frost-covered surface, can be explained almost entirely by their different orbital and rotational configurations. Pluto orbits the Sun freely with a high axial tilt that drives extreme seasonal variations. Triton orbits Neptune with a different geometry and experiences additional energy input from tidal heating. Give both worlds the same starting materials and the same building blocks, and their different orbital circumstances produce the surfaces we observe. The underlying worlds are the same kind of object. An earlier study by Kathleen Mant and colleagues at NASA's Goddard Space Flight Center examined the chemical compositions of Pluto and Triton in detail and concluded that the two bodies likely originated in the same region of the outer solar system. Both contain large amounts of nitrogen and carry substantial methane and carbon monoxide. Their volatile inventories are consistent with formation in the cold outer nebula that surrounded the young Sun 4.5 billion years ago. The study found that the surfaces and atmospheres of both worlds are deficient in carbon compared to what their building block composition should provide, and that this deficit can be explained by the loss of methane through a combination of aqueous chemistry reactions involving liquid water in a subsurface ocean and atmospheric processes. The carbon went somewhere, processed by interior chemistry, hinting that both worlds possess subsurface liquid water at some point in their histories. Triton and Pluto are, in essence, twins. Not identical, their histories diverged violently when Neptune's gravity intervened, but born from the same population of icy bodies, in the same cold region of the forming solar system, assembled from the same raw materials. One remained free, the other was captured, and that divergence in fate made all the difference. The question of how Neptune captured a body this large has occupied planetary dynamicists for decades. The problem is not trivial. Gravitational capture of a free-flying object requires that the object lose energy. An object approaching a planet on a hyperbolic trajectory coming in from interplanetary space has more than enough energy to escape the planet's gravity. It swoops in, curves around the planet, and flies back out again. To stay, it must shed energy during the encounter. Something must slow it down just enough to convert a hyperbolic flyby into a bound orbit. For tiny objects, several mechanisms can accomplish this. Drag from a circumplanetary gas disk can slow a small body. A collision with an existing moon can absorb kinetic energy. Tidal dissipation during an extremely close passage can extract orbital energy. But for a body the size of Triton, roughly 2,710 kilometers across, with a mass of approximately 2.14 times 10 to the 22nd kilograms, these mechanisms face serious challenges. Triton is too massive for gas drag to work efficiently. A collision with an existing moon capable of slowing Triton sufficiently would likely be catastrophic enough to destroy both bodies, and tidal dissipation during a single temporary capture passage may not extract enough energy quickly enough to prevent Triton from escaping again before the orbit is fully bound. The most widely accepted solution was proposed by Craig Agnor of the University of California, Santa Cruz, and Douglas Hamilton of the University of Maryland in a 2006 paper published in Nature. Their model invokes the disruption of a binary Kuiper Belt object. Binary systems are remarkably common among the large Kuiper Belt objects. Pluto itself has Charon, a companion roughly half its diameter. Surveys of the Kuiper Belt have found that a significant fraction of the larger bodies exist in binary or multiple object systems, gravitationally bound pairs or groups orbiting each other as they travel around the Sun. The formation of such binaries is a natural outcome of low-velocity collisions and gravitational interactions in the early Kuiper Belt. In the Agnor and Hamilton model, Triton was originally one member of such a binary pair. The two bodies orbited each other as they followed their path through the outer solar system. At some point, likely during Neptune's outward migration through the Kuiper Belt, when close encounters between the planet and large icy bodies were frequent, this binary passed close to Neptune. The planet's powerful tidal gravity pulled harder on the nearer member of the binary than on the farther one. The differential force exceeded the mutual gravitational binding energy of the pair. The binary was torn apart. One member was flung away, accelerated by the exchange of energy, and ejected onto a new, faster orbit that carried it out of Neptune's gravitational reach. The other member, Triton, lost energy in the exchange. It decelerated just enough to become gravitationally bound to Neptune, falling onto a highly eccentric retrograde orbit. The capture was brief, but gentle by cosmic standards. No physical collision was required, no destruction of Triton's structure, just a gravitational transaction. One partner lost, one orbit gained. This model is elegant because it exploits a mechanism binary disruption that is known to occur, and that involves objects of exactly the sizes relevant to Triton. It does not require improbable fine-tuning or exotic physics. The event would have been brief, violent in gravitational terms, but not destructive to Triton's physical integrity, and would naturally produce the kind of eccentric retrograde orbit from which Triton's current nearly circular retrograde orbit could evolve through subsequent tidal dissipation. The planetary migration context makes the probability even more favourable. Neptune was encountering many binaries during its sweep through the primordial Kuiper Belt, giving it numerous opportunities for exactly this kind of exchange. But if the binary disruption model is correct, it raises a question the audience will already be asking. What happened to the other one? When Neptune tore the binary apart, Triton was the member that lost energy and stayed. The other member, Triton's gravitational partner, potentially a body hundreds of kilometers across, possibly larger, gained energy. It was accelerated and flung away from Neptune on a faster trajectory than the one it arrived on. It did not disappear. It went somewhere. Several fates are possible. The ejected partner may have been scattered into the distant Kuiper Belt or the scattered disk, where it could still orbit the Sun today under a name we have already catalogued without knowing its history. It may have been thrown onto such an extreme orbit that it drifts in the far outer solar system, too faint and too distant to detect with current surveys. Or the energy kick may have been large enough to eject it from the solar system entirely, sending it into interstellar space as a rogue body, one of the countless free-floating objects that drift between the stars, unbound to any sun. We do not know which of these fates occurred. We do not know the size of the lost partner, its composition, or its current location. We may never know. The event happened billions of years ago, and the ejected body has had the entire age of the solar system to travel to wherever it is now. But the binary disruption model makes a concrete prediction. Somewhere in the outer solar system, or somewhere in interstellar space, there is a world that was once gravitationally bound to Triton, a companion that shared its orbit around the Sun until Neptune intervened and tore them apart. Triton kept a planet. Its partner lost everything. It is worth noting that alternative capture scenarios continue to be explored. A 2024 study by Rodney Gomes and Alessandro Morbidelli proposed a fundamentally different origin, that Triton was originally a regular prograde satellite of Neptune, one that formed in place, like a normal moon, and that its orbit was subsequently flipped to retrograde by giant collisions between Neptune and Earth-sized protoplanetary embryos during the planet's formation. Their numerical simulations showed that the likelihood of achieving a retrograde orbit through this mechanism depends heavily on Neptune's axial tilt after the collisions. This model remains a minority view. It is creative and physically plausible in specific scenarios, but it requires conditions that are difficult to verify independently. The binary disruption capture hypothesis remains the leading explanation. Whatever the mechanism, the consequences of Triton's arrival were catastrophic for everything already orbiting Neptune. When Triton was first captured, its orbit was not the nearly circular retrograde path it follows today. Capture from an external trajectory necessarily produces a highly eccentric orbit, a stretched ellipse that swings far from the planet at its farthest point and plunges deep into the inner satellite system at its closest. On this eccentric orbit, Triton would have crossed the paths of any pre-existing prograde moons with every revolution. A large body on a retrograde, eccentric orbit passing through a system of smaller prograde moons is a recipe for destruction. The encounter velocities between Triton and any existing moons would have been enormous. The retrograde motion means they would have been approaching each other head-on, adding their orbital speeds rather than subtracting them. At such velocities, even gravitational perturbations short of direct collision can fling smaller moons onto wildly altered orbits, sending them crashing into Neptune, hurling them out of the system entirely, or driving them into collisions with each other. Raluca Rufu and Robin Canup demonstrated this in a 2017 study using N-body simulations. They modelled a freshly captured Triton, interacting with a primordial prograde satellite system, similar in mass to the current satellite system of Uranus. The results were decisive. In a substantial fraction of their simulations, Triton's gravitational interactions destroyed or scattered the original moons. The retrograde intruder destabilized orbit after orbit, moon after moon, until the original prograde system was effectively erased. This explains why Neptune's satellite system looks so impoverished compared to those of the other giant planets. Jupiter, Saturn, and Uranus each possess multiple large and mid-sized moons in orderly prograde, orbits the natural products of in-situ formation. Neptune possesses Triton, and almost nothing else of significance. The other giant planets kept their original families. Neptune lost its family when Triton arrived. The Rufu and Canup simulations also showed that the interactions between Triton and the existing moons helped circularize Triton's orbit faster than tidal dissipation alone could accomplish. As Triton scattered and collided with the original satellites, it transferred energy and angular momentum. Its orbit shrank and became less eccentric. The moons absorbed the energy that Triton shared and were destroyed in the process. In a grim sense, the original moons gave their lives to settle the intruder into its current orbit. But not every original moon was destroyed, and a stunning piece of new evidence published just weeks ago may have identified a survivor. In May of 2026, a study led by Matthew Belyakov of the California Institute of Technology and published in Science Advances presented James Webb Space Telescope observations of Nereid, Neptune's third largest moon. Nereid has been a puzzle for decades. It orbits Neptune on an extraordinarily eccentric path. Its distance from the planet varies between roughly 1.4 million kilometers and 9.6 million kilometers over the course of each 360-day orbit. This wild eccentricity was traditionally attributed to a capture origin. Nereid, like Triton, was assumed to be an outsider grabbed from the Kuiper Belt. The Webb observations told a different story. Using the telescope's near-infrared spectrograph, Belyakov's team measured Nereid's surface composition in detail for the first time. What they found was a surface dominated by water ice, crystalline water ice, with features consistent with carbon dioxide. Nereid was bright, highly reflective, and spectrally blue. Crucially, when the team compared Nereid's spectral signature against a library of 54 Kuiper Belt objects, also observed by the James Webb Space Telescope, a true apples-to-apples comparison using the same instrument, Nereid did not match. Its surface was too water-rich, too bright, and compositionally too different from known Kuiper Belt bodies. Instead, Nereid's spectrum resembled the regular satellites of Uranus moons that formed in place around their planet. The implication was striking. Nereid does not look like a captured Kuiper Belt object. It looks like a moon that formed at Neptune. The team then ran dynamical simulations of Triton's capture and its interaction with a hypothetical primordial Neptunian moon system. In approximately 20% of the simulations, one of Neptune's original moons was not destroyed or ejected, but was instead flung into a highly eccentric, distant orbit, an orbit that closely resembled Nereid's actual path. The simulations showed that Nereid's bizarre orbit could be a direct consequence of Triton's arrival. Not a signature of capture from outside, but a signature of violent scattering from inside. Nereid was not a fellow intruder. It was a native refugee, the sole intact survivor of a moon system that Triton demolished. The study noted that Neptune's 7 small inner moons, Naiad, Thalassa, Despina, Galatea, Larissa, Hippocamp, and Proteus, are also likely survivors, but not intact ones. Voyager. 2 images show them as small, irregularly shaped bodies. They appear to be disrupted rubble piles, rather than primordial worlds, fragments, and reaccumulated debris from the collisions that destroyed the original satellite system. These inner moons may be second-generation objects, formed from the wreckage of the moons Triton destroyed. This picture of Neptune's moon system is extraordinary in its violence and its clarity. Before Triton arrived, Neptune likely possessed an orderly set of prograde moons, similar to what Uranus has today. When Triton was captured, it carved through this system like a wrecking ball, scattering and destroying moon after moon. The original system was annihilated. Only Nereid survived intact, flung to a distant eccentric orbit where it still circles Neptune today, carrying a compositional signature that links it to the planet's original family rather than to the distant Kuiper Belt. The small inner moons formed later, reassembled from the rubble, and Triton itself, the cause of all this destruction, settled into its circular retrograde orbit, dominating more than 99.5% of the system's total satellite mass. Triton is not just a captured object, it is a conqueror. It erased an entire moon system and replaced it with itself, and it brought something with it from the Kuiper Belt, a composition, an interior structure, a volatile inventory that Neptune's own moons would never have possessed. The frozen nitrogen, the methane, the carbon monoxide, the rocky core wrapped in water ice, all of this came from the outer solar system, carried inward by a body that never belonged to Neptune and still shows its foreign origin in every measurement we take. The capture also did something to Triton itself. It did not arrive and simply freeze into place. When Triton was first captured onto its eccentric orbit, it did not simply settle into a quiet new home. Every close pass by Neptune subjected it to extreme tidal forces that pumped heat into the interior on a massive scale. The energy of orbital circularization was not lost harmlessly into space. It was absorbed by the ice, by the rock, by the deep interior of a world that had spent its entire prior existence frozen solid in the outer solar system. The consequences of that absorbed energy, as we will see, may have produced a global subsurface ocean and driven geological activity that persists to the present day. The stolen world was not merely captured, it was transformed by the capture. The violence of arrival did not just destroy Neptune's original moons, it reshaped Triton from the inside out, heating a frozen Kuiper Belt world into something far more complex and far more active than it would ever have become on its own. And the evidence of that transformation is written across Triton's surface in terrain so young it should not exist, in geysers that should not erupt, in an atmosphere that should not survive, and in hints of an ocean that should not persist this far from the Sun. That evidence is what Voyager 2 flew through in 1989, and it is what no spacecraft has examined since. Triton should be dead. Not dead in the colloquial sense, dead in the geological sense. A world this far from the Sun, this small, this cold, should have exhausted whatever internal heat it possessed billions of years ago. It should have frozen solid from crust to core. Its surface should be ancient, saturated with impact craters, accumulated over 4.5 billion years of bombardment, a pock-marked record of every rock and ice fragment that ever struck it. It should look like Callisto Jupiter's outermost Galilean moon, an icy world whose surface is one of the most heavily cratered landscapes in the solar system, a place where geology stopped billions of years ago, and nothing has moved since. Triton looks nothing like Callisto. Triton looks like a world where something is still happening. When Voyager 2 swept past in August of 1989, it photographed a surface that stunned planetary scientists. The images revealed a terrain that was not merely unusual, it was defiant. It violated the expectations that scientists had carried across 12 years and 4 billion kilometers of spaceflight. The moon at the edge of the solar system was supposed to be a frozen relic. Instead, it was one of the most geologically complex surfaces ever observed. The first thing that struck researchers was the absence of craters. Impact craters are the default texture of old surfaces in the solar system. Mercury is covered in them. Earth's moon is covered in them. Mars, Callisto, Ganymede's older terrain, the moons of Uranus, everywhere you look at ancient surfaces, you see craters. They accumulate over time at a roughly predictable rate. The more craters a surface has, the older it is. A surface with very few craters is a surface that has been erased and rebuilt, resurfaced by some geological process that covered or destroyed the older terrain. Triton's visible surface has strikingly few impact craters. The estimates vary depending on assumptions about the impact efflux in the outer solar system, but the broad conclusion is consistent. The terrain Voyager 2 imaged is approximately 10 to 100 million years old. For a world that has existed for 4.5 billion years, a surface age of 10 to 100 million years is almost nothing. If you compress Triton's entire history into a 4,000-page book, the current surface would occupy the final page. Everything before that page has been overwritten, erased, replaced by whatever processes are reshaping this world. Something has been resurfacing Triton, and doing so recently enough that the evidence of ancient bombardment is almost entirely gone. But before examining what the surface looks like, it helps to understand just how cold this world is, because the geological activity Voyager 2 discovered does not merely defy expectation, it defies the physical conditions under which it occurs. Triton's surface temperature of approximately 38 Kelvin, minus 235 degrees Celsius, is not cold in any way that human experience can intuitively grasp. It is colder than liquid nitrogen, which boils at 77 Kelvin. It is colder than the surface of Pluto, which averages around 44 Kelvin. It is cold enough that oxygen, if present, would not be a gas or even a liquid. It would be a frozen solid, as hard as rock. Carbon dioxide would be a rigid crystalline mineral. Methane would be stone. At 38 Kelvin, the only common volatile that retains any capacity to sublimate to transition from solid directly to gas is nitrogen, and even nitrogen does so only barely. The vapor pressure of nitrogen ice at this temperature is vanishingly small. The thin atmosphere that results is measured in microbars, a pressure so negligible that it would register as a hard vacuum by any industrial standard on Earth. This is the thermal environment in which Triton's geology operates. Whatever processes resurface the terrain, whatever drives the geysers, whatever cycles, nitrogen between frost and atmosphere, all of it happens at temperatures where virtually every substance known to chemistry is locked in a solid state. Activity at 38 Kelvin is not merely surprising. It requires explanation. Energy must be entering the system from somewhere, because the surface temperature alone provides almost none. The terrain itself is extraordinary. Voyager 2's cameras captured a landscape of bewildering variety across the 40% of the surface that was illuminated and visible during the flyby. The southern hemisphere tilted toward the sun at the time of the encounter was dominated by a brilliant polar cap of frozen nitrogen. This cap was highly reflective, bright enough to give Triton one of the highest albedos of any body in the solar system. Nitrogen ice at these temperatures is translucent, and the cap's brightness comes from the way frozen nitrogen scatters sunlight. The boundary of the cap was not smooth, it was irregular, with tongues and lobes extending northward, suggesting active deposition and sublimation processes, nitrogen condensing from the atmosphere onto the surface in some areas, and evaporating back into the atmosphere in others. North of the polar cap, the terrain transitioned into one of the most enigmatic landscapes in planetary science, the cantaloupe terrain. Named for its resemblance to the skin of a cantaloupe melon, this region consists of roughly circular depressions, approximately 25 to 30 kilometers across, separated by ridges covering extensive areas of the image surface. Nothing like it exists anywhere else in the solar system. The formation mechanism remains debated, but the leading hypothesis involves diaporism, a geological process in which buoyant material from deeper in the crust rises upward through denser overlying material, deforming the surface as it pushes through. On Earth, diaporism produces salt domes, where buried salt deposits rise through heavier rock over millions of years, creating dome-shaped intrusions. On Triton, the buoyant material would not be salt, but low-density ices, perhaps nitrogen or methane ices, or mixtures of water ice and ammonia rising through a denser water ice crust. Each dimple in the cantaloupe terrain may mark the location where a plume of buoyant ice punched upward from depth, deforming the surface into a characteristic depression. If this interpretation is correct, the cantaloupe terrain is not merely a surface feature. It is a window into active processes in Triton's interior, evidence that material has been moving between the deep crust and the surface on a global scale. Other researchers have suggested that the terrain formed through repeated cycles of freezing and thawing in a volatile rich crust, or through a process analogous to the polygonal convection cells seen in Pluto's Sputnik Planitia. Whatever the cause, the terrain is geologically young and structurally complex. Beyond the cantaloupe terrain, Voyager 2 imaged smooth plains that appeared to have been flooded by cryogenic material, not liquid water, but flows of nitrogen, ammonia, or water-ammonia mixtures that erupted onto the surface and solidified. The most prominent of these is Cipango Planum, an extensive resurfaced plain in the southern hemisphere. The plain's surface is remarkably flat and nearly devoid of craters, indicating that whatever material covers, it was deposited in the geologically recent past, perhaps within the last few million years. The smoothness and extent of Cipango Planum suggest that the flooding was not a localized event. Large volumes of cryogenic fluid or viscous ice slurries appear to have erupted from the interior and spread across the surface, burying older terrain beneath a fresh layer. This is cryovolcanism in the most literal sense, volcanism driven not by molten rock, but by melted or mobilized ice, erupting from a cold interior onto a colder surface. If such eruptions have occurred repeatedly across Triton's post-capture history, they could explain the remarkably young surface age across much of the observed terrain. Ridges, fractures, and linear features cross the surface in multiple orientations, hinting at tectonic stresses that cracked and shifted the icy crust. Some of these features resemble the extensional fractures seen on Europa, where tidal stresses from Jupiter flex the ice shell and open cracks that are later filled with material from below. On Triton, the fractures may record a similar process, stresses from tidal forces, or from the global expansion and contraction of the ice shell as internal temperatures changed over time. Taken together, the surface features tell a story of ongoing energy release, and there is a number that puts this story into sharp quantitative focus. Scientists have estimated Triton's surface heat flux, the rate at which thermal energy escapes through the crust, by analysing how quickly surface features relax and flatten under gravity. On an icy world, topographic features gradually sag and smooth out at a rate that depends on the ice temperature, and the ice temperature depends on how much heat flows upward from the interior. The relaxation of Triton's observed surface features implies a heat flux on the order of 10 to 100 milliwatts per square metre. That range may sound abstract until you compare it to another world. Europa, Jupiter's ice-covered moon, the target of the multi-billion-dollar Europa Clipper mission, the flagship ocean world of modern planetary science, has an estimated surface heat flux of approximately 50 milliwatts per square metre. Triton's estimated heat flux overlaps directly with Europa's. The two worlds are releasing comparable amounts of energy through their surfaces. Europa's heat flux is considered one of the strongest pieces of evidence that its interior remains warm enough to maintain a global liquid water ocean. If Triton's heat flux is genuinely in the same range, the implications for its interior are the same. This single comparison reframes Triton's status among the ocean world candidates. It is not merely a theoretical possibility that Triton harbours a subsurface ocean. The thermal energy escaping through its surface is consistent with the energy levels that sustain confirmed or strongly suspected oceans elsewhere in the solar system. The data does not prove an ocean exists, but it places Triton squarely in the category of worlds where an ocean is physically expected. But the most dramatic discovery on Triton's surface was not a terrain type or a heat measurement. It was active eruption. Voyager 2 observed at least 4 geyser-like plumes erupting from Triton's southern hemisphere. The two best documented eruptions appeared as narrow columns of dark material, rising vertically from the surface to an altitude of approximately 8 kilometers. At that height, the material fanned out into horizontal clouds that drifted downwind for over 150 kilometers before settling back to the surface as dark streaks and deposits against the bright nitrogen frost. The rising columns were narrow, estimated at several tens of meters to roughly 1 kilometer in diameter at their base, but their vertical reach was remarkable. 8 kilometers is significant for any world. On a body with Triton's weak gravity, approximately 8% of Earth's launching material to that altitude requires either substantial pressure or sustained energy input from below. The dark streaks left by these plume deposits were visible across broad areas of the southern polar cap. Voyager 2 imaged numerous such streaks, oriented consistently in the same direction, indicating that prevailing winds in Triton's thin atmosphere carried the erupted material westward after it was lofted to altitude. The number and distribution of dark streaks suggested that the geyser-like eruptions were not isolated events. They appeared to be a recurring phenomenon, happening frequently enough to leave a visible imprint across hundreds of kilometers of terrain. The mechanism driving the plumes has been debated since the day the images arrived on Earth. Two broad categories of explanation have been proposed, and both may contribute. The leading exogenic model is the solid-state greenhouse hypothesis. At the time of Voyager 2's flyby, Triton was near the peak of its southern summer. The plumes were concentrated between approximately 50 and 57 degrees south latitude, a zone receiving intense solar illumination by Triton standards. Frozen nitrogen on the surface is partially transparent to visible sunlight. The hypothesis proposes that sunlight penetrates the upper layer of nitrogen ice and is absorbed by darker material dust, organic particles, or carbon-rich compounds embedded beneath the surface. This absorbed energy heats the subsurface, vaporizing nitrogen ice in a confined space. As the gas pressure builds, it eventually ruptures the overlying ice cap and explodes upward through the surface, carrying dark particles and nitrogen gas to altitude. A temperature increase of less than 4 Kelvin above the ambient surface value of approximately 38 Kelvin is sufficient to generate the pressures required to drive material to 8 kilometers. The energy source is the sun feeble at 30 astronomical units, but enough to trigger eruptions in a material as volatile as nitrogen ice at these temperatures. The alternative endogenic model proposes that the plumes are driven by internal heat rather than solar energy. Under this interpretation, the eruptions are a form of cryovolcanism. Material heated by geothermal processes in Triton's interior rises through the crust and erupts at the surface. This model connects the plumes to the broader evidence of geological activity on Triton. The young surface, the resurfaced plains, the tectonic features. If Triton possesses an internal heat source, residual tidal heating, radiogenic decay in the rocky core, or both, then cryovolcanic activity driven from below is physically plausible. The truth may involve elements of both. The solar greenhouse mechanism elegantly explains the geographic concentration of the observed plumes at subsolar latitudes, but it does not easily account for all of Triton's resurfacing activity, much of which occurs in regions and terrain types that do not obviously depend on solar illumination. The endogenic model provides a broader explanation for the young surface and the extensive cryovolcanic plains, but it must explain how enough internal heat persists in a world this small and this cold, this far from any major tidal forcing at its current near-circular orbit. That question, where the heat comes from, leads directly into the interior. Triton's thin but genuine atmosphere is another piece of evidence that the world is not geologically dead. The atmosphere is predominantly nitrogen, with trace amounts of methane, and has a surface pressure of approximately 14 microbars. This is extraordinarily thin, roughly 1/70,000th of Earth's surface pressure. A human standing on Triton's surface would not perceive the atmosphere in any physical sense, and yet it is real, measurable, and dynamic. The atmosphere exists because of a vapor pressure equilibrium between the nitrogen ice on the surface and the nitrogen gas above it. At Triton's surface temperature, nitrogen ice sublimates into gas at a rate that maintains this tenuous atmospheric layer. The process is seasonal. As Triton's orientation relative to the Sun changes over Neptune's 165-year orbital period, different regions receive more or less sunlight. Nitrogen frost sublimates in warmer areas and recondenses in colder areas. The atmosphere breathes, expanding and contracting, thickening and thinning, cycling nitrogen between surface ice and atmospheric gas on timescales of decades. Ground-based observations have tracked changes in Triton's atmosphere over time. Stellar occultation measurements, observations of distant stars as Triton passes in front of them, have revealed that Triton's atmospheric pressure increased between the Voyager 2 flyby in 1989 and subsequent observations in the 2000s. The atmosphere was becoming denser, likely because warming in Triton's southern hemisphere was sublimating additional nitrogen from the polar cap. This is not a static world with a frozen, unchanging envelope. The atmosphere responds to thermal conditions that evolve over decades and centuries. Perhaps the most puzzling atmospheric observation is Triton's ionosphere. Voyager 2 detected an ionosphere, a layer of electrically charged particles above the neutral atmosphere that was roughly 10 times more active than those of any other moon in the solar system. Ionospheres are typically powered by solar ultraviolet radiation, which strips electrons from atmospheric molecules. But Triton receives approximately 900 times less solar energy than Earth. The ionospheric activity Voyager 2 measured cannot be easily explained by solar energy alone. Some additional energy source, possibly magnetospheric interactions with Neptune's magnetic field, or charged particle bombardment from Neptune's radiation environment, must be contributing. The exact mechanism remains unresolved more than 3 decades after the measurement. Every observation points toward a world that should be dead but is not. The young surface, the geyser-like plumes, the dynamic atmosphere, the anomalous ionosphere, all of it demands energy. Energy to resurface terrain, energy to drive eruptions, energy to cycle volatiles. Where does a world this small, this distant, this cold find the energy to stay active? The answer begins with what happened to Triton's interior during and after capture. When Triton was first captured into its eccentric retrograde orbit, it was subjected to ferocious tidal forces. On each close pass by Neptune, the planet's gravity flexed and deformed Triton's interior, stretching it along one axis, compressing it along another, generating friction within the ice and rock. This friction dissipated orbital energy as heat, enormous quantities of heat. The energy extracted from Triton's eccentric orbit did not vanish. It was deposited inside the Moon, warming the interior from within. A 2024 study by Noah Hammond and Jeffrey Collins modelled this thermal and orbital evolution in detail. Their coupled thermal orbital simulations tracked how Triton's orbit evolved from its initial highly eccentric captured state to its present nearly circular configuration, and how the interior temperature profile responded at each stage. The results were remarkable. During the early phase of orbital circularization, tidal heating was intense enough to melt vast quantities of ice within Triton. The simulations showed that Triton developed a thick, global subsurface ocean, a layer of liquid water between the icy surface crust and the rocky core below. This ocean formed rapidly after capture and persisted for billions of years. The ice shell above the ocean was thin during this early epoch, thin enough for active convection, geological deformation, and chemical exchange between the surface and the liquid water beneath. The study found that as Triton's orbit circularized and tidal heating diminished, the ocean slowly cooled and the ice shell gradually thickened. But the process was far slower than earlier models had estimated. Tidal heating kept the ice shell thin and geologically active for a remarkably long duration, potentially several billion years. The subsurface ocean did not vanish quickly after the orbit became circular. Instead, radiogenic heating from the decay of radioactive elements in Triton's rocky core continued to supply warmth, maintaining the ocean long after the primary tidal heating episode ended. The study's conclusion was direct. Triton likely had a thick, long-lasting subsurface ocean that persisted for most of its post-capture history, and that ocean may still exist today in a reduced but present form. This conclusion is supported by independent modelling. Earlier studies examined the role of Triton's obliquity, its axial tilt relative to the orbital plane, in generating ongoing tidal heating. Triton's high orbital inclination of approximately 157 degrees means its orientation relative to Neptune creates obliquity-driven tides that, while far weaker than the tides generated during initial orbital circularization, are not negligible. If a liquid water layer exists beneath the ice, these obliquity tides can dissipate heat within the ocean itself, generating an additional energy source that slows the freezing process. One study estimated the ocean heat production rate at approximately 0.3 terawatts for a 300-kilometer thick ice shell, a modest but meaningful energy source capable of influencing ice shell dynamics and surface geology. The case for a present-day ocean received further support in 2026. A study published in Geophysical Research Letters by Wyville and colleagues analysed the magnetic induction signal that Neptune's magnetic field would produce in a conductive subsurface ocean at Triton. Neptune's magnetic field is unusual. It is strongly tilted relative to the planet's rotation axis and offset from the planet's centre. As Triton orbits through this complex and asymmetric magnetic environment, the changing magnetic field induces electrical currents in any conductive layer within the Moon, such as a salty ocean. These induced currents generate their own secondary magnetic field that a magnetometer on a future spacecraft could detect. The study showed that the induction signals at Triton are complex and time-dependent, with significant power at both Triton's orbital period and Neptune's rotational period. The signals are strong enough to be clearly distinguishable from background noise by a spacecraft carrying a sensitive magnetometer. Critically, the shape and amplitude of the induced field response would be diagnostic. The signal looks fundamentally different depending on whether Triton has a global ocean, a regional sea, or no liquid water at all. A future orbiter or even a well-instrumented flyby could resolve the question. This is not a theoretical abstraction. The tools to detect Triton's ocean exist. The measurement techniques have been proven at Europa, where the Galileo spacecraft detected an induced magnetic field consistent with a subsurface ocean. The challenge is not technology. The challenge is getting a spacecraft there. The potential habitability implications are significant. A subsurface ocean in contact with a rocky core, as Triton's internal structure suggests, provides the two key ingredients for potential habitability as we understand it: liquid water and a source of chemical energy. Water-rock interactions at the ocean floor can produce hydrogen and other reduced compounds through a process called serpentinization. Oxidants from the surface produced by radiation processing of surface ices can be transported downward through the ice shell via geological processes especially if the shell is thin enough for convection and fracturing. The combination of reduced chemicals from below and oxidants from above creates a chemical gradient, an energy source that, on Earth, sustains entire ecosystems of microbial life in deep-sea hydrothermal vents far from any sunlight. But how plausible is this ocean as an actual environment where chemistry could become complex enough to support life? The details matter. Triton's ocean, if it still exists, is almost certainly not pure water. Ammonia is expected to be present in significant concentrations, based on Triton's Kuiper Belt origin and the volatile inventories observed in similar bodies. Ammonia acts as a powerful antifreeze, lowering the freezing point of water substantially. A water-ammonia mixture can remain liquid at temperatures far below 0 degrees Celsius, perhaps as low as -97 degrees Celsius for the concentrations modelled in Triton's interior. This is brutally cold by terrestrial standards, but it is not beyond the limits of known biochemistry. Laboratory studies have found that terrestrial enzymes can catalyze reactions at temperatures down to -103 degrees Celsius. Life on Earth has not been found at these extremes, but the chemistry that supports life does not shut down entirely. The comparison to Enceladus is instructive. When the Cassini spacecraft flew through the plumes, erupting from Enceladus's south polar region, it detected not just salty water but silica, nanoparticles, and molecular hydrogen, both strong indicators that hot water was reacting with rock on the ocean floor. Enceladus's ocean is in direct contact with a silicate core, and that contact drives hydrothermal chemistry. Triton's ocean would be in the same configuration, liquid water resting on a rocky interior. The specific chemistry would differ because of Triton's different composition, temperature, and pressure conditions, but the fundamental architecture is the same: water touching rock, with energy flowing through the system. The Hammond and Collins 2024 study emphasized this point. Their simulations showed that Triton's ice shell was thin and geologically active for billions of years, increasing the likelihood of widespread exchange between the surface and the ocean. The transport of oxidants from the surface into the subsurface ocean would enhance the habitability of that ocean, supplying potential organisms with a continuous source of chemical energy. The authors concluded by arguing that Triton should be considered a primary target for future exploration due to its astrobiological potential, its geological activity, and its unique origin. The NASA Outer Planets Assessment Group has identified Triton as the highest priority candidate ocean world for future investigation. This ranking places Triton alongside Europa and Enceladus worlds, where the evidence for subsurface oceans is stronger and more direct, but where the scientific questions are similar. Can liquid water persist beneath an ice shell far from the sun? Can chemical energy support biological processes in a sunless ocean? Can a world that was never designed to be habitable become so through the accident of gravitational capture and tidal heating? Triton is not Europa. It does not have the dramatic plume activity of Enceladus, where geysers spray ocean water directly into space for spacecraft to sample. The evidence for Triton's ocean is modelled rather than directly observed. The plumes Voyager 2 saw may be solar-driven surface phenomena rather than expressions of deep interior processes. The uncertainty is real. But the uncertainty is also a product of ignorance rather than evidence against. We have visited Triton exactly once, with instruments designed nearly 50 years ago, for less than a day of close approach. We have imaged 40% of the surface. We have never measured the magnetic field with sufficient precision to detect an induced signal. We have never sampled the plume material to test for salts or organics. We have never mapped the surface at the resolution needed to distinguish cryovolcanic flows from solar-driven frost processes. Almost every question about Triton's interior, its ocean, and its activity remains open not because the evidence points to a dead world, but because we have not yet gathered the evidence that would resolve the question either way. What we do know is this: a world that should be geologically dead is not. Its surface is young. Geysers erupt from its frozen plains. A thin atmosphere cycles nitrogen between ice and gas. An ionosphere glows with energy whose source is not fully understood. The heat escaping through Triton's crust matches the heat escaping through Europa's. Models of its interior consistently predict a subsurface ocean created by the violence of capture, sustained by radioactive decay and residual tidal heating, potentially persisting to the present day. And the tools to confirm or refute that ocean exist right now, waiting for a mission that has not yet been built. Triton is a frozen world that refuses to be dead. And the reason it refuses is the same reason it orbits backward, the same reason it destroyed Neptune's original moons, the same reason its surface looks nothing like it should. It was captured, it was heated, it was transformed. Everything strange about Triton flows from a single event the moment Neptune's gravity reached out and stole a Kuiper Belt world from its original path. What that theft created, and what it means, is the last thing left to tell. There is a clock running inside Triton's orbit. It started the moment Neptune's gravity captured this world and set it moving backward, and it has not stopped since. Every revolution Triton completes around Neptune, once every 5 days and 21 hours, bleeds a small quantity of energy from the orbit through tidal interactions with the planet. Because Triton moves retrograde, against the direction of Neptune's rotation, the tidal exchange works in reverse compared to a prograde moon. Instead of gaining energy and spiraling outward, as Earth's moon does, Triton loses energy and spirals inward. The orbit contracts. The distance between Triton and Neptune shrinks. This is not a theoretical concern. It is an observed consequence of retrograde orbital dynamics, confirmed by the same physics that governs every tide on every world in this solar system. Triton is falling toward Neptune, slowly, imperceptibly on human timescales, but continuously, and without any mechanism that could reverse the process. The terminal point of this inward spiral is Neptune's Roche, limit the orbital distance within which tidal forces from the planet exceed the gravitational cohesion holding a moon together. Cross the Roche limit and the moon can no longer maintain its structural integrity. It is pulled apart. The material spreads into a ring. The world ceases to exist as a coherent body. For decades, the timeline for this event was thought to be relatively short by cosmic standards. Early calculations based on rough estimates of Neptune's tidal dissipation suggested Triton would reach the Roche limit in approximately 3.6 billion years, a span comparable to the remaining main sequence. Lifetime of the Sun. This raised the dramatic possibility that Neptune might one day gain a ring system rivaling Saturn's, composed of the pulverized remains of a world larger than Pluto. A 2025 study changed this picture substantially. Refined modelling of how energy dissipates within Neptune's interior produced a much lower tidal dissipation rate than earlier estimates had assumed. Under these updated parameters, Triton's orbital decay proceeds far more slowly. The revised timeline places Triton's arrival at the Roche limit approximately 28 billion years from now, roughly 6 times the current age of the solar system, and far beyond the point at which the Sun will have exhausted its hydrogen fuel, expanded into a red giant, and collapsed into a white dwarf. Triton will outlast the Sun. It will outlast the inner solar system. It will continue orbiting Neptune, backward, inward, long after Mercury, Venus, Earth, and Mars have been consumed or scattered by the Sun's death throes. The destruction written into Triton's orbit is real, but so distant in time that it belongs to an epoch of the universe that no star currently burning will survive to witness. This revised timeline does not diminish the significance of the orbital decay. It reinforces it. The slow inward spiral is permanent. There is no equilibrium state for a large retrograde moon, no stable endpoint, only a gradual, irreversible contraction that will continue for longer than the cosmos has existed so far. Triton is a temporary feature of Neptune's system, not temporary on human timescales, not temporary on geological timescales, but temporary on cosmological ones. It will end. The physics guarantees it. But the most immediate consequence of Triton's situation is not its distant future. It is its present obscurity. We have seen 40% of Triton's surface. The other 60%, the hemisphere that faced away from Voyager 2 during the 1989 flyby, has never been observed by any spacecraft at any resolution. It is the largest unexplored solid surface in the solar system between the Sun and the Kuiper Belt, larger than the unseen faces of any asteroid, any comet, any inner moon, 60% of a world, 2,710 kilometers in diameter, millions of square kilometers of terrain about which we know absolutely nothing. We do not know whether the cantaloupe terrain extends across the entire globe or is confined to one hemisphere. We do not know whether additional geyser-like plumes erupt on the far side. We do not know whether the unseen hemisphere contains different terrain types, features that might reveal different geological processes, different epochs of resurfacing, different clues about the interior. We do not know whether the most geologically interesting part of Triton is the part we have already seen or the part we have not. Triton is a book sitting in a locked room. We have read the spine and glimpsed a few pages through the keyhole. The rest remains closed. The Trident mission concept was designed to open that book. Proposed for NASA's Discovery program, Trident would have launched in the mid-2020s, used Jupiter's gravity as a slingshot, and arrived at Neptune and Triton in 2038. A single flyby, but a far more capable one than Voyager 2's. Trident would have mapped nearly the entire surface using wide-angle and narrow-angle cameras, far exceeding Voyager 2's 40% coverage. It would have carried an infrared spectrometer to map surface composition in detail. A magnetometer would have measured the magnetic field environment around Triton with the precision needed to detect an induced magnetic signal from a subsurface ocean. A plasma spectrometer would have sampled Triton's ionosphere directly, probing the mysterious energy source that makes it so anomalously active. The mission would have flown within 500 kilometers of Triton's surface, close enough to skim the upper atmosphere, close enough to sample charged particles, close enough to detect the faint magnetic whisper of a hidden ocean. And critically, it would have arrived before 2040, while the Sun's position still illuminated the same southern regions Voyager 2 observed. This timing would have allowed direct comparison between the two encounters nearly 50 years apart, revealing whether the geyser-like plumes were still active, whether the surface had changed, whether the geological processes Voyager 2 glimpsed were ongoing or had ceased. In 2021, NASA selected two Venus missions, the Atmospheric Probe mission and the Orbital Radar Mapper over Trident and the Io Volcano Observer. Trident was not chosen. The launch window it had targeted passed. The next comparably efficient Jupiter gravity assist opportunity for a Neptune-Triton trajectory will not occur for approximately 13 years. As of 2026, no mission to Neptune or Triton is funded, approved, or scheduled by any space agency on Earth. Other concept studies exist. The Triton Ocean World Surveyor, a New Frontiers-class mission concept, would orbit Neptune and make repeated close flybys of Triton, building up global surface maps and magnetic field measurements over time. Nautilus, another concept, targets similar science objectives. The Planetary Science Decadal Survey has consistently ranked a Neptune system mission as a high priority for future exploration. But priorities compete with budgets, and the outer solar system competes with destinations that are closer, cheaper, and faster to reach. The result is a world that sits at the intersection of some of the most important questions in planetary science: the origin of captured moons, the geology of ocean worlds, the habitability of icy bodies, the history of the outer solar system, and that has been visited exactly once, for less than one day, with instruments designed before most of the scientists who study it today were born. Consider the context. Europa is the target of the Europa Clipper mission, launched in 2024, which will conduct dozens of close flybys to characterize its ice shell, ocean, and habitability. Enceladus is a leading candidate for a future life detection mission, following the Cassini spacecraft's discovery of water-rich plumes erupting from its south pole. Titan was visited by the Huygens lander in 2005 and is the target of the Dragonfly mission, a rotorcraft that will fly through Titan's thick atmosphere and land at multiple sites across its surface. Even Pluto-Triton's compositional twin, the sibling that was never captured, was visited by the New Horizons spacecraft in 2015, which returned detailed images and data that transformed our understanding of this dwarf planet. Triton has received none of this attention. It remains the least visited, least studied major body in the outer solar system relative to its scientific importance. It is arguably the most overlooked ocean world candidate, not because the evidence for its ocean is weak, but because the evidence has never been tested by a mission capable of resolving the question. And yet Triton belongs in the same conversation as Europa and Enceladus, perhaps more urgently than some realize. Europa's subsurface ocean is supported by strong evidence: the induced magnetic field detected by the Galileo spacecraft, the young fractured ice surface. The the salt deposits visible in surface spectra. Enceladus provides the most direct evidence of any ocean world. Plumes of salty water erupt from cracks near the South Pole, sampled directly by the Cassini spacecraft and found to contain silica nanoparticles and molecular hydrogen, both indicators of hydrothermal activity on the ocean floor. Titan's subsurface ocean is inferred from the Moon's obliquity and the way its surface decouples from its interior during rotation. Triton's ocean is modelled rather than directly detected, but the models are robust, grounded in well-understood physics, and consistent across multiple independent studies. The tidal heating during orbital circularization was more than sufficient to melt the interior. Radiogenic heating from the rocky core provides ongoing energy. The obliquity-driven tides in a liquid water layer contribute additional heat. The 2024 coupled thermal orbital evolution model by Hammond and Collins showed that the ocean persisted for billions of years and may still exist today. The 2026 magnetic induction study by Wyville and colleagues demonstrated that a future spacecraft could detect or rule out this ocean using existing measurement techniques. What sets Triton apart from the other ocean world candidates is not the strength of the ocean evidence, it is the origin story. Europa formed in place around Jupiter. Enceladus formed in place around Saturn. Titan formed in place around Saturn. Their oceans, if they exist, were produced by the same tidal and radiogenic processes that shaped all the moons in their respective systems. They are natural features of the environments where these moons were born. Triton's ocean, if it exists, was created by capture. It was not part of Triton's original design as a Kuiper Belt object. A free-floating icy body in the outer solar system does not generate enough internal heat to maintain liquid water. Triton's ocean is a consequence of violence, the tidal energy released when Neptune dragged this world onto a new orbit and flexed its interior for hundreds of millions of years. Without capture, there is no ocean. Without the ocean, there is no resurfacing, no geysers, no thin ice shell exchanging material between surface and depths. Everything that makes Triton geologically interesting and potentially habitable is a product of the same event that makes it orbitally strange. This connection between orbital disruption and potential habitability is one of the most profound ideas in modern planetary science. It suggests that habitability is not a fixed property of a world determined at birth. It can be created later, imposed from outside, by gravitational events that were never part of the original plan. A frozen dead Kuiper Belt object can be converted into a warm, active, potentially habitable ocean world simply by being captured into the right orbit around the right planet at the right time. If this happened to Triton, it may have happened elsewhere. The solar system's history was violent, planets migrated, orbits were reshuffled. The Kuiper Belt was scattered and depleted. Objects were exchanged between regions. If binary disruption capture is a viable mechanism, and the modelling suggests it is, then other ice giants and gas giants in other planetary systems may have captured their own Tritons. Exomoons torn from their original trajectories, heated by tidal forces, transformed into ocean worlds that would never have existed without the accident of capture. Consider the arithmetic. The Kepler Space Telescope and subsequent exoplanet surveys have revealed that Neptune-sized and sub-Neptune-sized planets are among the most common types of worlds in the galaxy. They appear around a substantial fraction of all stars. Many of these planets orbit in regions where icy bodies would have been abundant during their system's formation epochs. If even a small percentage of these ice giants underwent migration episodes similar to Neptune's and dynamical models suggest migration is common, not exceptional then, close encounters between giant planets and icy bodies would have been widespread across the galaxy. Not every encounter results in capture. Not every capture produces conditions for an ocean. But the sheer number of opportunities is staggering. Billions of Neptune-like planets around billions of stars, many of them migrating through debris-rich environments early in their histories, encountering countless icy bodies along the way. Even if the probability of a Triton-like capture is low for any single system, the galactic total could be enormous. There may be billions of captured ocean moons in the Milky Way alone. Worlds that were never built to be habitable but became so through the accident of gravitational theft. This changes the arithmetic of habitability in a way that is easy to understate. When scientists estimate the number of potentially habitable worlds in the galaxy, They typically count planets in the habitable zones of their stars, the orbital band where liquid water could exist on a surface. That calculation misses subsurface oceans entirely. It misses Europa, it misses Enceladus. And it misses every captured moon in every planetary system where tidal heating converted a frozen body into a warm, wet world beneath an ice shell. If capture-created ocean moons are common, and Triton is evidence that the mechanism works, then the number of potentially habitable environments in the galaxy could be far larger than traditional estimates suggest. The habitable zone around a star may matter less than the capture zone around a giant planet. We cannot yet detect exomoons with current technology, but the principle Triton demonstrates that capture creates habitability, expands the potential for life in the universe in a way that formation-only models do not account for. It means that any icy body in any star system could become habitable if the right gravitational encounter occurs. The universe does not need to build ocean worlds from scratch. It can make them after the fact. Triton also forces us to reconsider what we mean when we call something a moon. The word carries an implication of belonging. Earth's moon belongs to Earth. It formed from the debris of a giant impact early in Earth's history. It has orbited our planet for 4.5 billion years. It stabilizes Earth's axial tilt. It drives the tides. It is part of the Earth system in a physical and historical sense. The Galilean moons belong to Jupiter. Saturn's moons belong to Saturn. They formed in their planetary systems, share their planet's angular momentum, and have been gravitationally connected to their host worlds since the beginning. Triton does not belong to Neptune in this sense. It was not born in Neptune's circumplanetary disk. It does not share Neptune's rotational angular momentum, it opposes it. It did not co-evolve with Neptune over the age of the solar system. It arrived from elsewhere, destroyed what was there, and settled into an orbit that is slowly decaying. Calling Triton a moon of Neptune is technically correct. It orbits the planet. It is gravitationally bound, but it obscures the deeper truth. Triton is a captured dwarf planet, a Kuiper Belt refugee, a world whose identity predates its current address. When we look at Triton, we are not looking at a product of Neptune's formation. We are looking at a product of the Kuiper Belt's formation, a body assembled from the same primordial ices and rocks as Pluto, Eris, Marche, and the thousands of smaller objects that still orbit beyond Neptune today. Triton carries the chemical and physical fingerprints of a birthplace that has nothing to do with the planet it now circles. Its nitrogen ice, its methane, its carbon monoxide, its rocky core, its bulk density, all of these connect it to the cold outer reservoir of the solar system, not to the ice giant it orbits. In a sense, Triton is the only piece of the Kuiper Belt that we have ever studied up close from orbit. The New Horizons spacecraft flew past Pluto in 2015, but it was a brief flyby, a single pass, a few hours of close approach, and then gone. No spacecraft has orbited a Kuiper Belt object. No spacecraft has lingered in the Kuiper Belt long enough to study any of its worlds in sustained detail. But Triton, a Kuiper Belt object that happens to orbit a planet, sits in a location that a spacecraft could reach and orbit. Not orbit Triton directly, but orbit Neptune, using the planet as a gravitational anchor for repeated close flybys of its captive moon. The same strategy that Europa Clipper will use at Jupiter, the same strategy Cassini used at Saturn. A Neptune orbiter with Triton as its primary target would not just study a moon, it would study a captured Kuiper Belt world in unprecedented detail, mapping its surface globally, measuring its magnetic environment to detect or rule out an ocean, sampling its atmosphere and plume material for chemical signatures, tracking its geological activity over time. It would answer questions about Triton and questions about the Kuiper Belt simultaneously. It would connect the study of ocean worlds to the study of the outer solar system in a way no other mission could. And it would do something else. It would look at the evidence of what capture did not just to Triton, but to everything around it. The shattered remains of Neptune's original moon system, the rubble pile inner moons, the lone intact survivor, Nereid, flung to its distant eccentric orbit, the debris that may have formed Neptune's faint rings, all of this is the aftermath of a single event, the arrival of a world that did not belong. and all of it remains poorly understood because no spacecraft has examined it since 1989. The outer solar system guards its secrets behind distance and time. Neptune is 4.5 billion kilometers from Earth. Signals traveling at the speed of light take over 4 hours to reach it. A spacecraft using current propulsion technology requires over a decade to arrive, even with gravity assists from Jupiter. The missions are expensive, the timelines are long, the engineering challenges are severe. Every year that passes without a funded mission to Neptune is another year that Triton's questions go unanswered. But those questions are not minor. They sit at the heart of some of the deepest problems in planetary science. How do moon systems form and evolve? What happens when gravitational capture reshapes a planetary neighborhood? Can tidal heating create habitable conditions on worlds that were never designed to support them? How common are subsurface oceans in the outer solar system? What does the chemical composition of a captured Kuiper Belt object tell us about the building blocks of the early solar system? Is Triton's ocean, if it exists, a plausible environment for life? These are not niche questions. They connect to the broadest themes in space science: the origin of water, the distribution of habitable environments, the potential for life beyond Earth, and they all converge on a single world, orbiting backward around a blue ice giant at the edge of the planetary system, waiting. Every few years, a planetary science conference session or a white paper or a mission concept study revives the argument for returning to Neptune and Triton. The scientific community consistently ranks the Neptune system among the highest priority targets for future exploration. The case is not controversial. Virtually no one in the field disputes that Triton deserves a dedicated mission. The barrier is not scientific. It is practical funding, scheduling, the long lead times required for outer solar system missions, the competition from closer and cheaper targets. But Triton is not going anywhere. It will still be there when the next generation of spacecraft is built. It will still be orbiting backward. Its surface will still be young. Its atmosphere will still cycle nitrogen between ice and gas. Its interior will still harbour whatever warmth remains from a capture event that happened billions of years ago. And its unseen hemisphere will still wait in darkness, holding answers to questions we have been asking since Voyager 2 flew past and left us wanting more. Here is what we know, stated plainly, with the uncertainties acknowledged. Triton orbits Neptune retrograde. This is confirmed by direct observation and is not in dispute. It is the only large moon in the solar system that does this. Triton was almost certainly captured from the Kuiper Belt. This is the consensus interpretation, supported by the retrograde orbit, the surface composition, the bulk density, and the chemical similarities to known Kuiper Belt objects, particularly Pluto. The leading capture mechanism is binary disruption, though alternative models exist and continue to be explored. Triton's capture likely destroyed or scattered Neptune's original prograde satellite system. This is supported by dynamical simulations, and by the 2026 James Webb Space Telescope, finding that Nereid's composition is inconsistent with a Kuiper Belt origin and consistent with formation at Neptune. Nereid may be the sole intact survivor of the original moons. Triton's surface is geologically young, approximately 10 to 100 million years old, based on crater counts from Voyager 2 imagery. Active geyser-like plumes were observed during the flyby. The driving mechanism, solar greenhouse versus endogenic cryovolcanism, remains debated. Triton possesses a thin nitrogen atmosphere that is dynamic and seasonally variable. Its ionosphere is anomalously active for a moon this far from the Sun. Thermal models consistently predict that Triton developed a global subsurface ocean during orbital circularization, and that this ocean may persist today, maintained by radiogenic heating and residual tidal effects. Direct confirmation requires a future mission with magnetometer and geodetic measurement capabilities. No mission to Neptune or Triton is currently funded or scheduled. The Trident Discovery-class mission was not selected in 2021. Concept studies for future missions continue, but no launch date has been set. These are the facts. They are incomplete. They are bounded by uncertainty. And they describe one of the most remarkable worlds in this solar system. Triton does not belong to Neptune the way other moons belong to their planets. It was not born here. It did not form from the same material. It does not orbit in the same direction. It arrived from the outer solar system, a frozen world from the Kuiper Belt, a sibling of Pluto, and it was captured by Neptune's gravity in an event that may have involved the tearing apart of a binary system and the destruction of every moon Neptune had before. That capture did not just imprison Triton, it transformed it. Tidal forces heated the interior. Ice melted into a global ocean. The surface was reshaped by geological processes that continue to defy expectation. Geysers erupt. The atmosphere breathes. The terrain looks impossibly fresh on a world 4.5 billion years old. Everything about Triton that makes it scientifically compelling, its young surface, its plumes, its possible ocean, its astrobiological potential exists because of the violence of its arrival. It is a world defined by a single event. Capture created the ocean. Capture powered the geology. Capture destroyed the moons that came before. Capture wrote the backward orbit that is still, slowly, shrinking. Everything leads back to that moment when Neptune reached out and stole a wandering world from the cold darkness beyond. And now Triton waits. It orbits Neptune backward, carrying the frozen evidence of its foreign origin on a surface we have mostly never seen. It holds its secrets beneath a crust of nitrogen ice that we have never sampled. It harbours possibly an ocean that we have never detected. It is the only captured Kuiper Belt dwarf planet accessible to orbital study. The only ocean world candidate whose habitability was created by capture rather than formation, and the most scientifically important world in the outer solar system that has not been visited since the Cold War. Triton is not Neptune's moon in the way that word is usually meant. It is a prisoner, a stolen world. A piece of the deep outer solar system, trapped in orbit around an ice giant, still carrying the scars and the warmth and the frozen chemistry of a life that began somewhere else entirely. It does not belong here. The orbit says so, the composition says so, the destroyed moon system says so, and that is exactly what makes it extraordinary. I, the moon that should not belong to Neptune, is the moon that has the most to teach us about capture, about oceans, about the possibility of life in the darkest and most distant corners of the solar system. All we have to do is go back,